Hello, everyone, and welcome to our today's webinar about the THB, the Transient Hot Bridge. Before we start, some organizational information. So all of you participants are muted. So if you have any questions or comments, just use the chat or the question answer session, and I will answer all of your questions after the presentation. So yes, so if you have any questions, just type them into the chat and I will answer them at the end. So you can also type it in already during the current slide. If there are any problems, for example, the sound is off, just also use the chat for that and I will try to fix the problem. For your information, the webinar will be recorded, and after the webinar, you will get an email with the link to the recording and some further information to the webinar afterwards, probably tomorrow in the morning. We are also very happy to receive some feedback after the webinar, what you liked, what you disliked about the webinar, or if you have any special topics which you wish to be also discussed in a webinar, just send us an email with your feedback and your wishes to us. So I also want to introduce myself. My name is Erika Hahn. I'm here responsible at Linsize for the application measurements in our lab here with the topic thermoconductivity and thermoelectrics. So let's start with the webinar. Today's topic is the THB, the Transient Hot Bridge instrument, which is able to determine the thermoconductivity. For those who do not know Linsize yet, a short introduction. So Linsize Messgeräte GmbH is a family-owned company founded in 1956 by Dr. Maximilian Linsize, who you can see here on this picture. And now his son, Klaus Linsize, and two of his sons, Florian Linsize and Vincent Linsize, are leading the company. We have the manufacturing here located in Selb in northern Bavaria, but we also have own sales and service locations in the US, China, and India, and also more than 65 distributors worldwide. Our business area started with some data loggers, as you can see it here in this picture. But then the computer took over so that the data loggers are not needed anymore. So the company focused more on measuring instruments for thermal analysis, thermoconductivity, and thermoelectrics. And as already mentioned, we produce the instruments, but also have our service lab where we offer some measurements. So here you can see also a picture of one of our labs here in Germany. On this slide, you can see our product range. So we cover the classical thermal analysis like scanning calorimeters, thermal balances, STAs, and dilatometers. We also have instruments for thermomechanical analysis, also for thermoconductivity and diffusivity, but also for the characterization of thermoelectric materials and from the Hall effect, as well as a special application for the analysis of thin films in the nanometer or micrometer range. What is unique for Linsize is that we offer customized options. So there are several furnaces available for our instrument, and it is also possible to couple the instrument with some gas analyzers, for example. So we are very flexible regarding the application and open for customizations. This as a short introduction into the company. And now I will present to you what is the plan for today. First of all, I will have a look on to how in general determine the thermal conductivity. There are two basic method groups. I will introduce both of them. Then I will show you the THB in general, also which sensors available are for this instrument. Then how these sensors work, so what they are doing to determine the thermal conductivity. And then I will go a little bit more into details regarding the samples, their preparation, and also which accessories are available to realize different applications. Then we will have a look into the software, and in the end, there will be a summary. So let's start with the measurement methods. How to determine thermal conductivity in general. There are two groups, the transient methods and also the stationary methods. In all of them, the sample is subjected to a thermal disturbance. Within the transient measurement methods, one already has a look as soon as the thermal disturbance is brought into the material. So it can be seen here and also here in the changing temperature of the sample on this illustration. The stationary methods instead wait until there's a stable temperature gradient through the sample. So when the brought in heat flux corresponds to the going out heat flux of the sample. So this can be seen in here in this graph when you see here a straight line, a straight horizontal line. So the difference between both methods is that the transient methods really have a look into the sample as soon as the thermal disturbance is brought into the material and measures how the material changes and reacts to this brought in heat. And the stationary methods wait until everything reached a stable state. So this waiting time already suggests that the measurement takes rather long. So this is the disadvantage of some steady state methods, that the measurement time is rather long. Additionally, the steady state methods have a rather limited thermal conductivity range, so it is more focused for the insulation materials. Probably some of you know the guarded hot plate method or the heat flow meter, which are the typical steady state methods. And also our TIM tester belongs to this group of methods. Advantages with the steady state methods is that the data evaluation is rather easy and one has a very high accuracy because one really waits until everything is stable and then reads out the values. The transient measurement methods, because they already have a look when the sample temperature is changing, they are rather fast. So typically the measurement times are in some second or lower minute range. And the most common techniques which belong to the transient group are the hot strip, hot wire, hot plane, or transient hot bridge method, as well as the well-known laser flash method. These are all transient measurement methods. Advantages is that, as already mentioned, the measurement time is very low. Additionally, one can measure a very, very broad range of thermal conductivity, so from insulation materials to very high conductive materials. It is also possible to cover a very broad temperature range. But disadvantages is on the one hand that the theory is really complex as one has to model the heat transport properties of various materials in a short time, how it reacts to this thermal disturbance. Furthermore, especially with the laser flash method, one cannot determine the thermal conductivity directly, but firstly has only the thermal diffusivity. LINSIZE offers a broad range of thermal conductivity instruments. The heat flow meter, shortly HFM, and the thermal interface material tester belong both to the steady state methods. So these are both plate methods where one has two plates. One of them is cooled and the other one is heated, and a sample is sandwiched in between. And then one waits until the applied temperature gradient leads to a constant heat flow through the sample. All of these other methods are transient measurement methods. So the laser flash analyzer, the most universal instrument for thermal conductivity determination, as it covers a very broad thermal conductivity and a very broad temperature range. The THB is also suitable for a broad range of applications, and for thin films, we have the TF-LFA, which uses a similar technique to the LFA, and we also have the TFA, which is also used for thin film analysis. Here on this slide, you can see the different thermal conductivity and also temperature range of all of these just mentioned instruments. So one can see that the heat flow meter and the TIM tester focus more onto the lower conductive materials up to about 10 to 30 watt per meter Kelvin. And the THB and the laser flash instrument are covering more or less the complete thermal conductivity range. The laser flash has the advantage that it can measure to extremely high temperatures, so also up to 2800 degrees Celsius. Whereas the THB is limited up to 200 or 700, depending on the type of sensors. So with the THB, one is able to determine the thermal conductivity, but also thermal diffusivity of various materials. We have developed the THB with the German Metrological Institute, PTB, and launched our first instrument in 2011. Starting from 2021, we are offering an updated version of the THB where we improve the electronics and also the software so that the usage of it is improved. Now the THB looks like this. So the transient hot bridge instrument allows fast and easy measurement of thermal conductivity, also thermal diffusivity, and the specific heat capacity by calculation with density of solids, liquids, powders, and pastes in a very broad temperature range from minus 150 degrees to 700 degrees Celsius. You can see it also here in the thermal conductivity range that it allows the measurement of a lot of different materials. The instrument is available in 3 different models. The difference between those models, so the basic, advanced, and ultimate version, is the range of thermal conductivity which can be realized. As the instrument allows the measurement of a broad range of thermal conductivities, we need some different sensors to realize that. We have on the one hand Kapton-based sensors for the measurement up to 200 degrees Celsius, and we also have some ceramic-based versions which allow then the measurement up to 700 degrees Celsius. The advantage of the THB is that it is a plug-and-play system, so you can directly connect another type of sensor one after the other without changing the type of instrument. It's just a plug which you have to exchange to allow then the measurement of different thermal conductivities. So here the laminated THB sensors allow the measurement of solids up to 5 watt per meter Kelvin. The QSS sensor is for high conductive materials, also especially for solids. The metal-framed version of the THB sensor is especially suited for the measurement of solids, not solids, sorry, for liquids, powders, and pastas, also up to 5 watt per meter Kelvin. And for very small and especially also for anisotropic samples, we have the hot point sensor, which has only a very low sensor area. So here just the tip needs to be covered, which is about 2 × 2 millimeter. For the other sensors, there's the requirement that the sample needs to cover the complete sensor foil. So here for the THB sensor, we have two versions. One is about 25 × 45 millimeter, and the other, the larger sensor, has a sensor area of about 45 × 85 millimeter. The QSS sensor is also for about 25 × 55 millimeter large samples. So here also the requirement is that the sample covers more or less the complete sensor foil. Only for the hot point sensor, just the tip needs to be covered. On this slide, you see the ceramic version of all of these sensors. So for the THB version, we have a ceramic version, as well as for the high conductive materials, the QSS sensor. And the hot point sensor is divided into two groups, one for solids and one especially for liquids, powders, and pastas. These ceramic-based sensors allow the measurement up to 700 degrees, but one needs to keep in mind that the accuracy of the ceramic-based sensors is slightly low or is lower compared to the Kapton foil sensors, as here the substrate is rather thick compared to the Kapton foil, and one cannot exclude the thermal conductivity of the ceramics, so that here the accuracy is slightly lower. As you have seen, we have a broad range of different sensors. And here you can see why we have so many different sensors. Each of the sensors is for a different application. Advantages is that you just unplug one sensor and plug in the next sensor and can proceed with all of your measurements. So we have sensors which are especially suited for solids, for smaller samples, for larger samples, and for lower conductive to higher conductive samples, but also sensors for liquids, pastas, and powders, or for very small samples. So in the next slides, I want to go a little bit more into detail about the different type of sensors. As you have probably recognized, one can divide the sensors into three groups. Let's go maybe to this slide back again. So one group are the THB sensors. The next one is the QSS sensor, and the third group are the hot point sensors. So let's start with the THB sensors, which also gave the instrument its name. Yes, so the transient hot bridge sensor is a patented sensor, and as already mentioned, was developed with the German PDB Institute. It is suitable for fast and high accuracy measurements. One can determine the thermal conductivity, thermal diffusivity, and by knowing the density, one can also calculate the specific heat capacity of a material. It has a very low uncertainty because the hot wires are connected to a Wheatstone bridge, and this enhances the sensitivity. But how the sensor works, I will explain some slides later. Here you have the sensor size in more detail. the smaller sensor can measure up to 2 watt per meter Kelvin and the larger one up to 5 watt per meter Kelvin. And the Kapton foil-based sensors can go up to 200 degrees Celsius. The QSS sensor is especially suited for materials with a high thermal conductivity. QSS stands here for quasi-steady state. So the sensor measures a little bit different compared to the transient hot bridge sensor. So here we are not completely in the transient state, but are approaching the steady state. So it's more or less a mixture of the transient and the steady state measurement method. By that, one can combine the advantages of the steady state and transient measurement techniques, which allow then the measurement of the high thermal conductivities. As well as with the THB sensor, one can here determine the thermal conductivity, diffusivity, and also the specific heat capacity. It has a slightly lower uncertainty because here the calibration is also more crucial. So all of the sensor needs to be calibrated with a suited reference material. And as you see here, we have a very, very broad thermal conductivity range, and one needs to take care which calibration reference material one uses to have the highest possible accuracy of measurement. Our third group, or our third sensor, is the hot point sensor. It is especially suited for the measurement of small samples, so about 3 times 3 millimeters squared samples can be measured with it. Especially this is suited for anisotropic samples, where one can easily change the direction of measurement because only a small sensor area needs to be covered. Here you see again the pictures of the different sensors, so the Kapton foil-based version, the ceramic one for the solids, and here this long rod with the tip especially suited for liquids. Here you see an image taken by a microscope here of this tip, where you see then here the wires on the complete front. The hot point sensor can measure also low conductive materials up to materials with a thermal conductivity of 30 watt per meter Kelvin. So now you know that we have 3 different groups of sensors: THB, QSS, and hot point sensor, and you know for which kind of application one can use the different sensors. But how do these sensors work? The measurement principle is for all of the sensors the same, only the sensor layout is different for all of the groups, and these allow then the different applications. All of these sensors serve as a dual heat source and at the same time also as a resistance thermometer. So during the measurement, the sensor emits a constant heating current and heats itself. The temperature rise, recorded with the resistance thermometer, over time is then a measure for the thermal properties of the sample. So the transient measurement method, you bring in a thermal disturbance into the material and detect how the material reacts to it with time. Based on that, one can then determine the thermal conductivity. Especially for the THB sensor and the QSS sensor, which are connected to a bridge network, one does not measure the temperature increase directly, but one measures the bridge voltage, which is also directly proportional to the temperature increase. Here you can see an illustration. So during the measurement, one uses the sensor which is basically a hot wire and a thermocouple. The sensor needs to be completely surrounded by the material. So typically one needs 2 sample pieces and sandwiches the sensor in between. So then you sandwich the sensor in between. During the measurement, the sample will be heated by the hot wire, and the thermocouple recognizes a temperature increase with time. Based on that, one can determine the thermal conductivity. Here on this slide, you can see especially the working principle of our THB sensor. As already mentioned, it is based on the hot wire or hot strip method, but the THB sensor is an enhancement of it. Because the hot wire is not just a straight line as one strip, but meander-shaped and also separated into 2 parts with 4 of them connected to a Wheatstone bridge. We have a higher electrical resistance, compensate the end effects, and enhance the sensitivity compared to this basic hot wire setup. Because of that, also the accuracy of the THB sensor is higher compared to the basic hot wire method. So here you can see that 4 of these identical meander-shaped tandem strips are connected to each other to a Wheatstone bridge. And as already mentioned, we measure here the bridge voltage to be able to determine the thermal conductivity of a material. So you have already heard that the THB can measure the thermal conductivity of solids, liquids, powders, and pastes. Also, you already heard that the sensor surface needs to be completely covered by the sample, so one needs rather large samples for the analysis with the THB. As already mentioned 2 slides before, typically for solids, the sensor foil is sandwiched in between 2 sample pieces. So it's important that the sample surface is rather smooth so that they fit perfectly on top of each other so that there is no air in between those 2 sample pieces. To enhance the thermal contact between the sensor and the 2 sample parts, one typically presses the configuration together. One can use, for example, such a manual press for it. So that also, for example, compressible materials like foams can easily be measured without pressing the material too much together very easily. So in general, also the sample preparation is rather easy. You have 2 pieces, take one sample piece, the sensor and the next sample piece together, and then just press it together with such a manual press. Or one can also just put a weight on top of the configuration. So the sample preparation with solids is very easy. The same counts for the sample preparation of liquids, powders, or pastes. The easiest way is one just takes a beaker, fills in the liquid or the powder, and then hangs the sensor into the material. So on the picture here on the right, you can see a beaker full of water and the sensor, a THB sensor in the small version with a metal frame, which you cannot see due to the deflection. Here would be the metal frame, is inside of the liquid. So advantages for the THB is that you have a very simple sample preparation and can easily detect the thermal conductivity of also bulk and large materials, so you do not need to cut it into small exact samples. To allow the measurement of various materials, also in a defined temperature range, there is some furnaces available also in our product range. Here you can see the Peltier furnace, where you have here some Peltier cooled plates or Peltier heated plates, where you put in your sample sensor configuration, and here have the possibility, for example, to put also some weight on top. To be able to realize thermal temperature dependent measurements of the thermal conductivity, one needs an additional furnace because the sensor heating is not strong enough to approach, for example, 100 degree. The sensor heats up the sample only locally and for a few Kelvin. So the heating of the sensor itself of the sample is typically in the range of 1 to 4 Kelvin. So you cannot realize temperature dependent measurements just with the sensor. So one needs an additional furnace for this kind of application. This is also why the THB instrument is especially suited for room temperature measurements or measurements close to room temperature, because you can easily change the sample, so you can realize a measurement row very fastly at room temperature. There's also a tool for the control of the contact pressure. So for example, for foams or elastic materials, one can also realize pressure-dependent measurements. As for elastic materials or soft materials, the thermal conductivity strongly depends on the contact pressure. I also have put in an application example a few slides later, where you see how strongly the thermal conductivity can depend on the contact pressure. For solids, you have this manual press, more or less as a sample holder, but for liquids and powders, we also offer a sample holder. Here you can see pictures of our powder sample holder. It is such a container where you fill in your material, bring in the sensor from the side, and then fill it up with the powder. And then you can also close it and realize also pressure-dependent measurements. For liquids, there's also a special sample holder available to easily realize this kind of application. What is new since a few weeks, more or less, is the single-sided sensor. Here, the difference to the other sensors is that you only need just one piece of sample. So as mentioned before, typically for these foil sensors, you need 2 sample pieces to be able to sandwich the sensor in between. But with the single-sided sensor, you can also measure just one piece of sample. One side of the sample is then covered with some insulation material so that one can assume that there is a directed heat flow from the sensor directly to the sample. As you can see, here is the design visible of the QSS sensor. So it's more or less the QSS sensor within this single-sided setup. Advantages of the single-sided sensor is, of course, that you just need one sample piece. So typically one uses a sample piece, cuts it into 2 halves and sandwiches the sensor into the 2 pieces. But with this sensor, you do not need to damage or destroy your one sample piece to be able to realize a measurement. Additionally, one has fewer requirements for the sample surface, because for the 2 sample setup, you need 2 sample pieces, which fit perfectly on top of each other so that there's no air. Here you have only the requirement of one straight, smooth surface where the sensor can be put on top. It is, of course, also easy in handling and especially for the high conductive samples. So for metals, for example, it shows an improvement in measurement. As always, if there are some advantages, there are also some disadvantages. So the disadvantages of this single-sided sensor are that the measurement of low conductive materials, especially insulating materials, is not so easy and shows or is even not possible and shows a higher uncertainty. Furthermore, if one is interested in the thermal diffusivity, it will be also not possible with this, or not as good as possible with the sensor as with the classical two-sample setup. So these were the accessories and also our new single-sided sensor. And now let's have a look into the software. So first of all, you prepare your sample, put in the sensor in between two sample pieces or with the single-sided sensor on top of a material. And then you go to the PC and set up your measurement. The software is also very simple designed. So one has the possibility to store and recall some measurements. One sees information about the sensor. So as already mentioned, we have with the THB a plug-and-play system. So the software also automatically detects the type of sensor which is currently plugged in. You can read out the temperature which is measured by the sensor and start and control measurements here. One is also able to give some information about the measurement, and one sees directly the results in a table, which are also exportable as a Word file, PDF, or text file. And on the bottom, one sees the recorded measurement curve. Depending on the type of connected sensor, these curves look differently. So here on the left, you see the measurement curve of the THB sensor, and on the right of the QS sensor. For the THB sensor, we detect here in red the temperature increase, and blue shows the measured bridge voltage. Here on top, depending linearly on the time, and on the bottom, the time is plotted logarithmically, and we see here in blue again the bridge voltage, and the most important curve for the THB is shown here on the bottom in black. It is the derivative of the bridge voltage. During a measurement, one should record a curve which looks like that so that one can see an increase, a maximum, and a decrease of the derivative of the bridge voltage. From the maximum here, we calculate the thermal conductivity. From the decrease here, we can determine the thermal diffusivity. So one can also have a look onto the measurement and decide if the measurement was good or not, also within the software, just with one look. For the QSS sensor, we also detect temperature increase and the bridge voltage. On the bottom, one also sees then the derivative of it. The most important curve here is the upper blue one, so the bridge voltage, which is measured. One can see here that we are here in the clear transient state, so the temperature is changing, and in the later times we approach then a more or less steady state, so a more or less straight horizontal line is approached. From the measurement times, you can also see that the time is very short. Here with the THB sensor, PMMA was measured with a measurement time below 30 seconds. And with the QSS sensor, a titanium sample was measured with a measurement time of about 10 seconds. So, as already mentioned, the measurement time is very low. After the measurement is performed, one can also export the results in a Word file, which will look then similar to this one. So one will see here all the information about the sample and the used sensor. One will get the results in a table, where one is also able to perform 3 measurements, for example, or 10 measurements or 20 measurements in a row. And in the end, there would be then the average value also displayed in this table here. And also the measurement curves will be exported. But one can also just store the measurements and recall them later. In the next slide, here I will start a video where a PMMA sample was measured, so a polymer sample with a small THB sensor. So you see here on the top that a THB sensor was connected and the ambient temperature was about 22 degrees. So here, firstly, the report settings are typed in so that we are measuring a PMMA sample. And then you basically just need to click on Start. First, it will wait for a stable temperature distribution. And now what is also very nice with the THB, it first performs a short test measurement to be able to determine the best measurement settings for this kind of material. And now what you see here is the running measurement. So we see here on the bottom that the bridge voltage derivative is increasing, found its maximum and is decreasing. As soon as the measurement is finished, the result will plop up here in the window on the top. So this is also an important point here with the THB, that the measurement time does not need to be typed in by the user, but is determined automatically. Additionally, also the heating current of the sensor is also determined automatically for most of the sensors, so that the THB is also more or less a one-button solution where one just plugs in the sensor and clicks on Start. And in the last few slides, I want to show you some application examples. So here on this slide, a phase change material where some hydrated salts were measured in a temperature range from -20 to +30 degree, and a THB metal frame sensor was used to realize this. As you can see on the picture on the left, the sample was filled into a beaker. It was liquid and room temperature, and the sensor was hung into the material so that more or less the complete sensor foil was covered. And then the setup was put into a tempered liquid bath to control the temperature of the sample. Here you can see then the resulting thermal conductivity, which each show the average of 3 measurements at one temperature. What is clearly visible is that the thermal conductivity changes with the state of the material. So at room temperature and below room temperature, it was liquid, and below or around 0 degrees Celsius, it started to be solid. And here the thermal conductivity each is higher for the solid state compared to the liquid state. So with this application example, you can see that also the measurement of a solid and liquid can be both realized with the THB. And as already mentioned before, I want to show you also an application example of some soft insulation material under different compressions. But here we did not control the pressure force itself, but we adjusted the sample thickness using such a manual press so that we could have the material in different thicknesses. For this measurement, also a THB sensor was used, the smaller version, which is called in our company THB-B, which describes the smaller THB sensor. From the results, one can see that all of the three different tested materials show different thermal conductivities. So from the values, you see that this is really an insulation material, and one can see that all show a significant dependence on the sample thickness, so a significant dependence onto the compression of the material. So these are two application examples which I wanted to show you. And on the last slide, I want to summarize our THB. So our transient hot bridge instrument is an accurate measurement instrument for the determination of thermal conductivity and can also determine the thermal diffusivity and specific heat capacity. It is a plug-and-play system and more or less a one-button solution, as one can perform some automatic measurements where the measurement parameters are determined automatically. So it is very easy to use, as also the sample preparation is very simple, and one does not need experienced staff to be able to operate the instrument. Additionally, it's often not easy to be able to determine which property or which settings are the best to be able to measure the material. The THB can do this automatically so that the errors caused by some wrong measurement parameters will be lowered or will just not be there. The measurements can be performed very fast. So you have seen within the short video how long a measurement of a polymer, for example, takes. It's just about 30 seconds. Metals, for example, can be measured just within about 10 seconds. The maximum measurement time is typically within a few minutes, up to 3 or 4 minutes. With our new single-sided sensor, one does not need to cut a material into halves, so non-destructive measurements can be realized. Furthermore, the instrument is a very small and light tabletop instrument so that it can be carried around very easily. The THB is, in 2 words, a very easy to use instrument for the determination of thermal conductivity, allows the measurement of various materials like liquids, powders, pastes, and solids, and is very easy to use. It is a relative measurement method so that it needs to be calibrated, but the calibration is also not complex. What one does there is one just uses a suited reference materials and performs more or less just one measurement with it to be able to calibrate them at the sensor. So now I'm at the end of my talk. I want to thank you very much for your attention, and I'm now open to all of your questions. So if you have any, please type them into the chat. and I will answer them one after the other. So if you have any questions, just feel free to use the chat and type them in there. So during the presentation, one question came up, appearing on slide 20. So here on this slide, where I showed how the setup of a typical measurement looks like. The question concerns the measurement of liquids. So there are two questions. How do we clean the sensor to avoid contamination? The sensors are Kapton foil sensors. So it is a Kapton foil where in between two foils, the heating wires are located and everything is closed. So the sensor is basically just a Kapton foil, so it can be cleaned very easily. For that, one can use some standard solvents like acetone, isopropanol, or some other alcohols, for example. So you just wipe the Kapton foil so that it will be clean again. The second question there was, how do you measure the thermoconductivity of a liquid sample in a temperature range, for example, from 10 to 100 degrees Celsius? So the THB can easily adapt it into an already existing furnace. For example, in the lab, we also have a drying furnace where you just can put in the sensor and the beaker to be able to realize measurements, or as seen in one of the application examples, one can, for example, also use a tempered liquid bath where you just put in the beaker with the sensor. A further question which came up for solids, do we have requirements of surface finishing? So as already mentioned, the surface of a solid sample needs to be as smooth as possible. There's no number I can give you here, but if you touch the surface of the material, it should feel rather smooth. So this is necessary so that both of the sample pieces can really fit each other very good, so that there is no air gap in between those two material fragments. But it is in general also possible to measure slightly rough surfaces. If the surface is too rough or too scratchy, one can, for example, also put in a very thin layer of a copper paste or another thermal paste to smoothen out the surface. Typically, a very thin layer of such a paste does not influence the measurement itself too strongly, so that there's not too strong deviation of results due to the sample preparation. So one question was, so that when salesperson contact a customer, I will give that forward to my colleague and they will contact you. Thank you for also giving here the email address. I will note that down and they will contact you. Okay. So there was also a question that the evaluation and the measurement curves look very similar to the TPS method, so the transient plane sensor method. I think this is what TPS stands for. So as already shown here on this slide, in general, the sensor is based on this hot wire or hot strip method, or also on the TPS method. But this sensor layout, especially the one of the THB sensor, is an enhancement of it. So advantages of our THB sensor compared to, for example, the TPS method is that due to this bridge voltage, which is already built into the sensor, we have an enhanced sensitivity and thus an enhanced accuracy. With some other models, like for example, the TPS method, typically the bridge voltage, is not within the sensor, but within the instrument. And this is resulting in a lower accuracy and also in a more complex electronics. So the advantage of this bridge voltage here is the enhanced sensitivity. So there are coming up some further questions. So if any pressure is needed in the sensor sample sandwich, let me go to the slide with the photo. Sorry. Here you see that we typically need to press the configuration together. One does not need a too strong pressure, but just some light pressure so that one can enhance the thermal contact between the sample and the sensor. So typically, a pressure of 0.5 kilogram is enough. And then there was again asked about the difference between the 2 sample setup and the 1 sample setup. Here you can see an illustration of the 2 sample setup where you sandwich the sensor in between 2 sample pieces. The later shown half-shell sensor or single-sided sensor is just a sample, just one sample, and then the sensor on top. So it reduces the amount of samples. The difference is that the 2 sample setup is more universal for lower to higher conductive samples and has the higher accuracy. The single-sided sensor is especially suited for the high conductive samples, as one can more easily realize the measurement of thinner metallic or high conductive samples. There's also a question about, again, this automatic determination of the measurement parameters. As already mentioned, most of the work is done by the THB itself. So let us have a look again here into this video, where it is easy visible what the system does. So basically one can also perform some measurements manually. Here within the options, you can change the measurement time and the heating current, but the system does it also automatically. So here on the top, first sample information are typed in. Now start was clicked. Here on the bottom, you see a short waiting time for stable temperature. Let's pause this. Here on the lower left, you see trying to find optimum heating current. So short test measurement is performed. So it takes like 2 seconds, and now the actual measurement is done. So you have seen the user just had to click here on start, and everything is done automatically. So the measurement time and also the heating power is determined automatically. So it's a one button system where you just need to click on start. So with most of the sensors, one can perform automatic measurement. Yes, so if I have seen that correct, these were all questions which came up to now. So are there any further questions? So one further question came up. Let me just have a look. There's a question regarding the specific heat capacity measurement. So some of our competitors seem to have a special cell for specific heat capacity independent measurements. This we do not offer. We offer more or less only the determination of specific heat capacity within one run, at the same time with the thermal conductivity and thermal diffusivity. Here you can see that one can select the properties which should be determined. So one can have a look onto the thermal diffusivity. So the thermal conductivity is always determined. The thermal diffusivity can be determined with the THB sensors and also with the QSS sensors. If one has knowledge about the density, one can also determine then the specific heat capacity, because the thermal conductivity is the product of thermal diffusivity, density, and the specific heat capacity, and then you can calculate that. The highest accuracy we achieve with the THB in determining the thermal conductivity. The accuracy of the thermal diffusivity determination is slightly lower, so let's say about 5 to 7%, depending also on the material. And this then leads to also a similar uncertainty in the specific heat capacity. So with the THB, it's only possible to determine specific heat capacity in the calorimeter function, where one determines the 3 thermal properties at the same time. So there's not a specific cell for the specific heat capacity independent measurement. To have the highest accurate specific heat capacity, I would recommend to use a DC or a calorimeter in general, because here the system is then specified for the CP determination, whereas the THB is more focused on the thermal conductivity determination, but one has the advantage to also have a value for the specific heat capacity. It might be not the most accurate one, but one at least has an orientation with a rather low uncertainty. So there's also a question where the US office is located. You can find on our website where we have our offices. The US office is in Robbinsville, so not far away from New York. So if there are no any further questions, I want to thank you again very much for your attention and being here. We are also very happy to see you again in the next webinar, which will be about regulated humidity and water vapor and thermal analysis, which will be on the 15th of November, so in about a month. So if you are also interested in that topic, we are happy to see you again there. My colleague will be then the speaker of the next webinar. If there are any further questions about the THB, you can also contact us. Here's our website and our email address. Just write us an email and we will answer it as soon as possible to help you further with your questions about the THB or any other thermal analysis topic. So thank you again for being here. Just a short answer. There was one question about the recording. There will be a recording of this webinar, and this webinar will be provided to you probably tomorrow within an email. So thanks again and have a nice day. Goodbye.